Good evening, everyone. In my talk, I will tell you about some properties of automorphism of regular rooted trees related to growth. Groups acting on trees is a central object of study in geometric group theory. And the idea is that we can derive algebraic properties of groups from their action on trees. And this idea was quite fruitful, and for the last 50 years, many beautiful theories were developed. Let me mention a classical action of algebraic groups on their Broughat tree, Basser theory of groups acting on trees, constructions of non-residually finite lattices in the product of automorphism groups of trees, and even finite represented simple groups. And for my talk, this is an important class of actions on regular rooted trees, where we have Burnside groups, groups of intermediate growth. And the fundamental example here is the famous Grigorchuk group. Also, there are many classes of groups like automaton groups, or similar groups, iterated monodromic groups, and so on. So I will consider automorphisms of regular rooted trees. In a regular rooted tree, the tree has some degree d, and all other vertices have degree d plus 1. Now, as you can see on this picture, we can label vertices by words over a finite alphabet. So we can think of this tree as a space of words over alphabet. The space of words is the most self-similar object, and this self-similarity we can see in this tree. So if we take any vertex, and if we consider subtree hanging below this vertex, then this subtree is isomorphic to the whole tree. You just need to erase the prefix. And now this self-similarity of this tree is reflected in the self-similarity of the automorphism group of this tree. So for example, if we consider some automorphism, and this automorphism fixes this root, and suppose it fixes 0, then it should fix the whole the subtree, and it induces an automorphism inside the subtree, which you can think is an automorphism of the whole tree, because the subtree is isomorphic to the whole tree. But let me be more precise, and I need the notion of a state of an automorphism. So let G be an automorphism of our rooted tree. Take a vertex V. Then we define the state of G at V as the following automorphism. So G maps the rooted tree hanging below V to the rooted tree hanging below G of V. And now if you remove these prefixes, you get a map from X star to X star, and it will be again an automorphism of X star. So essentially, this automorphism, which we denote G restricted to V, describes the action of G after the prefix V. Now, when we have this notion of a state, we can define many interesting subgroups in the group of automorphisms. For example, we can consider automorphisms with finitely many states, finite-state automorphisms. And they form a group, the group of finite-state automorphisms. We may consider subgroups which are close with respect to taking states, which is called self-similar groups, and so on. And today, I will be talking about the number of states and how the number of states grow when you take the power of an automorphism. So let me, but before that, let me give another insight. So how we can see our tree inside our automorphism group. So this is our tree, but now for each vertex, we have a state, an automorphism. At the root, we have our automorphism G. At this vertex 0, we have our automorphism, some automorphism G restricted to 0, and so on. So at each vertex, we have an automorphism. And we can also label these edges by the action on the first letter. For example, if 0 maps to 1, then we label this as 0, 1, and so on. So we get something like a portrait of an element G. And now we can talk about, for example, width of this portrait. So we consider the level of this tree, and we consider how many different automorphisms are at this level. And for example, consider automorphisms with bounded width. Or if you consider finite state automorphisms, then in this infinite tree, we'll see only finitely many states. Then we can talk about the depths, after which we actually see all possible states. Again, if we consider finite state automorphisms, then we see a lot of repetition in this graph. But this is not necessary. Suppose G00 automorphism is the same as G. Then we can just remove this state and replace this edge to this vertex G. In this way, we get a finite graph which completely defines the action of our element G. And this finite graph is actually an automaton. And the number of states of this automaton is exactly the number of states of our automorphism. So as I said, every finite automorphism defines a finite automaton, and vice versa. Every invertible automaton defines a finite state automorphism. Here, I'm not going to define exactly what kind of automata I discuss, but you can see here two pictures, two automata. And so there are some states, there are some arrows, and the arrows are labeled by two letters of the alphabet. So I will consider such automata. And of course, and as usual in computer science, when you define automata, you actually define an initial state. So when I say that automaton defines a finite state automorphism, I mean that you have an initial state. But actually, every state defines some automorphism, and you can generate a group by such automorphism, and you get an automaton group. Now, automaton groups for the last 20 years found many interesting applications in different areas of mathematics, but I will mention only the result about groups of intermediate growth, the result which influenced all of this research. So this is a result of Rostislav Grigorchuk from 1983, that this automaton generates a torsion group of intermediate growth between polynomial and exponential. And this was the first example of a group of intermediate growth. Now, the growth function of a group counts the number of different elements represented by words of lengths at most n over generating set. And for this automaton, this growth function actually coincides with the growth function of automaton. And this growth function counts the number of states in the minimization of the composition of this automaton. So you consider n times iteration of automaton with itself, and then you minimize it and consider the number of states. Now, to find precise asymptotic behavior of the growth function for such a simple automaton happens to be a very difficult problem, which was solved only recently. In my talk, I will consider different growth function not of a group, but of an automorphism. So let G be a finite state automorphism. And we define the growth function as the number of states of G in power n. Or in terms of automata, if we have an automaton representing this automorphism, then we take n power of this automaton as initial, minimize it, and take the number of states. So this is quite similar to the growth on the previous slide. However, this time our automaton is initial. Now, this growth function has another natural interpretation. So if we have some function which is computed by some automaton, then we may wonder how many states do we need to implement composition of this function with itself n times. So nth iteration of this function. And our growth function exactly counts that exactly tell us what is the minimal number of states required to do this. Now, let me show you a simple example. So let's consider adding machine. So for the adding machine, adding machine. So this is a machine for adding of 1 in binary number system. It has only 2 states. Here you can see, so if the input word starts with 0, then you add 1. If it starts with 1, you replace it by 0 and then carry on adding 1. Now, we may ask, what is the minimal number of states to realize addition of n to binary number? So actually, what is the growth function of this adding machine? And of course, it depends on the binary expansion of n. And here you can see a precise value of this growth function. What we can notice is that the growth function is actually logarithmic. If the number of zeros here is large, then the growth function is close to log n. If the number of zeros is small, then if the first position, non-zero position is small, then the growth function is close to 2 log n. So the growth is logarithmic. However, if you divide by the logarithm, there is no limit. So this function oscillates between 2 logarithmic functions. Now, what can we tell in general about growth of finite state automorphisms? What are some basic properties? In general, it is not monotonic. It is bounded if and only if this element has finite order. And this property is not decidable algorithmically. If an automorphism has infinite order, then the growth function is at least logarithmic and at most exponential. So if for groups the bound is like linear and exponential, then for a finite state automorphism, the bound is logarithmic and exponential. And now I will consider growth for several classes of automorphisms. And the first one is the class of bounded automorphism, defined by Sitkin. So a finite state automorphism is called bounded if the number of words such that of length n, such that the section, the state at this word is non-trivial, is bounded by a constant independent on n. So in other words, among n, if you consider inputs of length n, there will be only finitely many, such that after processing this word, you end up in a non-trivial state. In terms of the action on a tree, this means that the action is concentrated along finitely many directions. So you'll see some non-trivial sections only along in the neighborhood of a finitely many directions. This class of automorphisms is pretty restrictive. However, all initial examples of automaton groups, like the Grigorchuk group, Basilica group, Hanoi Tower group on 3px, they all consist of bounded automorphisms. Now, what can we say about the growth of such automorphisms? They have an interesting property that the width of all powers of a bounded automorphism is bounded uniformly. So there's a constant c such that for any power n and for any level of this tree, the number of different states at this level will be bounded. So we have a bound on the size of the width of this tree. And the second property is that they have logarithmic depths, because bounded automorphisms are contracting, and that's why the depths of this tree will be logarithmic. And from this it follows that for every bounded automorphism of infinite order, the growth is logarithmic. So there are two constants c and d, different constants, such that the growth function oscillates between these two logarithmic functions. So it was interesting for me because like There is no natural class of automaton groups for which the asymptotic is known. But at the same time, we have a natural class of automorphisms for which we have asymptotic, and this is the smallest possible asymptotic, non-trivial, non-bounded asymptotic. So the next question was how hard is to compute the growth function and the automaton representation for G in power n. In general, if you take, how would you compute the minimal representation automaton for G in power n? So we take the automaton, we can compute nth power of this automaton and then minimize it. However, when you compute a in power n, you'll get exponential number of states. After that, exponential in n. So it will be double exponential in the input, in the size of n. And after that, you still need to minimize it. What we prove with my student Vladimir Skachko is that for every bounded automorphism, there exists an algorithm which, given n, computes the minimal automaton for G in power n and the growth function in, this is quadratic time, in the size of the input. And if this automorphism is transitive, then actually you can do it in linear time. Now, to construct such an algorithm, actually, as you can see, this algorithm depends on the bounded automorphism, because we don't know what is the complexity, how the complexity of the algorithm depends on the automorphism. But now, to construct such an algorithm, we need to solve certain problems for bounded automorphisms. Let me mention just what? That for any bounded automorphism, you can represent each state of each power of G in the following way. So there will be finite set of automorphisms such that Gn restricted to V is equal to A times B in power n. So A and B belongs to a finite set which depends on G. And you can construct the states step by step, and each state will be represented by A, B, and some power. So let me move to the next slide. So each state will be represented by A, B, and some integer number. And this triple represents the automorphism A, B in power n. And you construct them step by step. But then we need to solve the following problem. How do we know that these states are different? Maybe they define the same automorphism. So each time we construct a new state, we need to solve this equation. We need to check, is it true that these automorphisms are equal? Now, in general, the word problem is solvable for groups generated by bounded automorphism. And it is solvable in polynomial time. But the polynomial time is in the length of the input. So here, the length may be n, and it will be polynomial in n, which is not polynomial in the logarithm of n. So it will be exponential time, and you need to do it each time. What we prove is that there exists an algorithm which, given bounded automorphism A, B, C, D, decides whether this equation has a solution in Nm. Now, this is generalization of the order problem. And moreover, we have a description, some sort of a description of the solution set, such that given Nm, one can check this equation in linear time. And then it helps to solve and compute minimal representation in log n squared in quadratic time. Now, the next class of automata and automorphism I want to consider are polynomial automorphisms. They define similarly, except that the number of words where we see non-trivial state is bounded by a polynomial in N. And we say that an automorphism is polynomial of degree D if this number is bounded by a polynomial of degree D and not of degree D minus 1. Now here on this picture, you can see the simplest example of a polynomial automorphism of degree 1. Again, quite simple automaton, however, quite interesting group. Now, polynomial automorphisms are not contracting in general. So by this, I mean that the depth of the portrait is not logarithmic. And what I proved some time ago is that if we have a finite set of polynomial automorphisms of degree D, then we can bound the depth of any word of length n over the set by a polylogarithmic function. So it is not logarithmic, but it is polylogarithmic, some big contracting property. Now, if we consider growth of elements, then we can prove a slightly better estimate. Let G be a polynomial automorphism of degree D, then the depth of G in power n is log n times log n in power D. And the growth function of a polynomial automorphism is polylogarithmic, log n d plus 1 times additional log n. Now, yes, and for automorphisms that act transitively on levels, these terms are redundant. So basically, we need these terms to cover orbits, other orbits. Now, and for every D, we can construct polynomial automorphisms with this growth function. I'm not sure about this term, but this term is precise. And the construction uses free semigroups generated by polynomial automorphisms. Now, using this result, one can prove that for every polynomial automorphism, there exists an algorithm which, given n, computes the minimal automaton for G in power n in polynomial time. And still, I don't know if the order problem for polynomial automorphism is decidable. Oops, sorry. Now, another type of growth, another restriction that I want to consider is uniform bound on growth. So for bounded automorphism, we saw a nice property that first, they have logarithmic depth, and second, the width is uniformly bounded independently on n. And I started wondering, can we have a group such that the width is bounded independently on a group element? So what can we say about groups such that the width of every element of a group on every level is bounded by a constancy? And it happens that it's possible to describe such groups. But first of all, about logarithmic depth. There is a nice class of groups which guarantees that we have logarithmic depths. They are called contracting. So an automaton group is called contracting if the length of the section in terms of generators contracts exponentially. So there will be constant less than 1 such that the section at the first level is strictly smaller, and you can repeat this again and again. And eventually we have that portraits of all elements of contracting groups have logarithmic depths. And from this, we immediately deduce that the growth function for elements of contracting groups is polynomial. Now, about uniformly bounded widths. The result is the following. So let G be a self-replicating contracting group. Self-replicating is some additional technical property that is discussed here. Now, there is a constant C such that the width of all elements is bounded if and only if the group is crystallographic. Mm-hmm. Now, the theorem is actually non-trivial in both directions. And for crystallographic groups, this bound follows from the fact that these states are located in a neighborhood in some ball of radius r in a intersecting some lattice. And that's why it is bounded. In the opposite direction, we first prove that the group is virtually nilpotent, then study its conjugacy classes, and that it is not possible to have infinite conjugacy classes to prove that it is virtually abelian, and then restrict to crystallographic group. And finally, I wanted to show you one more example with a discrete Heisenberg group. Again, it can be represented as an automaton group, and here is some sort of a description of this automaton group. And now it is interesting that for this description, there exists a subgroup such that for all elements, the growth function is logarithmic. And for all other elements in this representation, the growth is linear. Finally, about exponential growth. So we saw many examples of classes where the growth is the smallest possible, like logarithmic or polylogarithmic. Now, there is actually an interesting class of automata for which the growth is exponential. These automata were defined by Makedonsky, Nekrashevich, and Sushchansky. I'm not going to give a definition, but I just say that here we consider those automorphisms such that you can extend it in a unique way to the full regular tree, not rooted. Now, there are many sources of bireversible automorphisms. They are related to square complexes, to lattices and product of trees, to some actions of algebraic groups on Brouatist trees. So this is a very interesting class of automata. And for many of these automata, I have checked, for example, for all groups that comes from some of these constructions, one can check that the growth is exponential. And actually, the growth series is rational. And in many cases, the growth of a bireversible automorphism coincides with the growth of the whole automaton. Because this follows from the fact that in many cases, when you consider the power of this automaton, it will be strongly connected. And then from each state, you have access to any other state. And that's why the growth of an initial automaton is equivalent to the growth as non-initial automaton. Nevertheless, I don't know if the growth is actually rational for every bireversible automata. This remains a question. Thank you.
Thank you.